Hopefully you've watched the first video on inverse functions where I explained what inverse functions are and how we can find them if we're given coordinate pairs, even if they're in the form of a graph or a table or mapping. We talked about how functions are inputs and outputs, and that an inverse function has these inputs and outputs reversed. Recall that if we have a function and its inverse, the inverse function will undo what the original function did. The inverse function essentially switches the inputs, the x's or the domain, and the outputs, the y's or the range. When we are asked to find the inverse of a function algebraically, we just have to follow these steps. We make sure the original function is a one-to-one using the horizontal line test. If not, then we restrict the domain so it will be 1. We replace the f of x with a y and then switch the x's and y's and then solve for y. At the very end, we replace the y with an f negative 1 of x, remembering that the restricted domain for the original will result in a restricted domain for a range for your inverse. In this example, our original is a linear function. As long as a linear function is not a horizontal line, it will always be a one-to-one function. So we do not need to work out restrictions for this. A says to find the inverse of x, and then once we have that, part B says to find the output if the input of the inverse is a -7. So let's start with part A. First thing we're going to do is replace the f of x with a y, and then switch all the x's and y's. After we switch the x's and y's, all we've got to do now is get the y by itself by using opposite operations. What we're going to end up with here is y is equal to x minus 3 over 2, and we're going to rewrite it with the f negative 1. We read that as f inverse of x is equal to x minus 3 over 2, or we could rewrite it as 1/2 x minus 3/2. All right, let's look at part B. In part B, they want us to use -7 as an input, but we're putting it into the inverse function. So we're going to replace the x with a -7, and then all we've got to do is simplify, and we'll get -10 over 2 or -5. So when we put a -7 into the inverse, we get a -5 out. Keep in mind what that means is that for the original, if we put a -5 in, we would have gotten a -7 out. Now if we take these function and the inverse function we just found, and then we rewrite them and find points using a table, these are the points we would get. And you notice how the x's and y's are just reversed. The inverse function just reversed the x's and y's for us. And again, if we were to plot these points, we're going to get this reflection over the y equals x line that we were looked at before. Now, in example 2, we've got another linear function. So we're going to go ahead and start with this. What we're going to do is we're going to switch the f of x and make it a y, and then we're going to switch the x's and y's and then solve for y. And again, we're just using inverse operations. We're going to add 1 to both sides, and then we're going to divide by 3. We end up with f inverse of x is equal to x plus 1 over 3. Or we can divide both the x and the 1 by 3 and get f inverse of x equals 1/3 x plus 1/3. On the left is a cubic function. F of x is equal to x to the third in blue. And its inverse, a cube root function, f of x is equal to the cube root of x in red. Note the blue function passes the horizontal line test, so it's a one-to-one function. Based on this, we know the inverse will also be a function. And if you look at the red function, it clearly passes the vertical line test, showing that it is a function. Now looking at the graphs on the right, the blue graph is f of x is equal to x squared. Looking just at the blue graph, it's clear this will not pass the horizontal line test. So we would expect the inverse not to be a function. And then looking at the red graph, you can see that it's not a function. It will not pass the vertical line test. We want the inverse to be a function. So our job now is to come up with a restriction on the domain of the original function that will result in a graph that it's a one-to-one. With quadratics, the easiest thing to do is to identify the vertex and limit the domain to a one-side. So in the case of y equals x squared, the vertex is going to be 0, 0. So if you limit the domain to be x being greater than or equal to 0, we're going to end up with only the one side of the quadratic's parabola. You'll notice how we just have the right side, the positive x's in the graph. Well, now when we find the inverse, what's going to end up happening is we're going to end up with a function, because the blue one, now that we've restricted the domain, is 1 to 1. And again, f of x is equal to x squared. It's pretty easy to find the inverse. We just switch the f of x to a y, switch places, and then square root both sides. And keep in mind, when you square root an equation, it should be plus or minus. But the thing is, in this case, we didn't use the whole function. We only used the one side. So our inverse is only going to have the one side. It's going to be the positive square root function. We're going to look at a couple more of these in a second. When you're asked to find the inverse of a function, very often all you're going to do is switch the x's and y's and then solve for y using inverse operations. It's not super difficult. However, there are some tricky ones, and we're going to look at some of those right now. This first one is a quadratic, but because it doesn't have a b term, it's not that tricky. But we do have to keep in mind that quadratics are never going to be a one-to-one function. They either going to open up or they're going to open down, but they're always going to fail the horizontal line test. Their inverse will not be a function. What we need to do is restrict the domain. So what we're going to do is we're going to find the vertex, and then we're going to pick one side of it and we'll use that as our domain. So to find the vertex, we just do negative b over 2a, or you can graph it in the calculator if you want. Once we find out that the x is equal to 0, we substitute in the 0 for all our x's, and we find out that our y is equal to 6. Our vertex is going to be 0, 6. Now, if I graph that, it's going to look something like this. And all I've got to do is, I'm just using the positive x's. That's going to be my domain. My domain is going to be all the x's that are greater than or equal to 0. So what's going to happen is it's going to just be half of the parabola, like we've shown in the graph. Now, we go and start the process. We switch the f of x to a y, and then we switch places. And all we've got to do is, like I said before, just get the y by itself using inverse operations. We can do this because this doesn't have a b term. And we'll look at another example of where it does in a minute. Anyway, when I square root both sides, typically I'm going to end up with plus or minus. I only used half of the quadratic to start with, so I'm only going to use half of this inverse. The question is which half, the plus half or the minus half? A positive square root function goes up like this, and a negative square root function, it starts and then goes down. In this case, our domain was all the x's are greater than or equal to 0. Well, for the inverse, what's going to happen is that our range is going to be all the y's are going to be greater than or equal to 0. And if the vertex 0, 6 is part of the original, well then 6, 0 has got to be a point on the inverse. So if I plot that, well, there's our point. And if it's either going to go up or down, well, if my range has to be the y's have to be greater than a 0, it has to go up. Well, I'm going to write the notation now. F inverse of x is equal to square root of x minus 6 over 2. And we don't need to put the plus sign in front. We're going to assume that it's positive. So it looks like this. And like all inverse functions, you notice how this is a reflection over the y equals x line. Okay, now let's take a look at finding the inverse of a quadratic that's in vertex form. Okay, number 5, the quadratic is written in vertex form. Now just looking at it, you may be thinking that this has got to be a whole lot harder to find the inverse of, but the truth is, it's only a little bit more difficult. Really, we do pretty much the same thing. Now, it's in vertex form, which you remember is y equals a times x minus h squared plus k, and then the vertex is hk. So the nice thing about this is when it's in vertex form, it's really easy to figure out the vertex. And because it's a quadratic, we know it's not going to be one-to-one. So we're going to identify the vertex so we can establish a domain that we're going to use. In this case, the vertex is going to be 3, 6, which we've graphed over here. Now we've got to figure out a domain, and we can pick either side of the vertex, either the bigger numbers bigger than that or less than that. In this case, we're going to go ahead and say that our vertex is going to be greater than or equal to 3. And so our half of our parabola is going to kind of look like this. Now, all we've got to do is switch this f of x to a y, and then trade the x's and the y's in the equation, and then get y by itself. And all we're going to do is inverse operations. We'll subtract 6 on both sides, giving us x minus 6 is equal to 2 times y minus 3 squared. And then we're going to divide both sides by 2, and we're going to get x minus 6 over 2 is equal to y minus 3 squared. And then the way we undo something squared is to square root it. So we'll square root both sides. And we have the plus or minus the square root of x minus 2 over 2 is equal to y minus 3. And then we'll add 3 to both sides, and then that's going to give us 3 plus or minus the square root of x minus 2 over 2. Now it's going to equal y, and like we did before, we've got two parts of this, a plus and a minus part. We only need one part of it. We only used half of the domain, so we only need half of the inverse. And remembering that the radical function will go up if it's positive and down if it's negative, well, that helps us figure out which one we're going to do. So let's take a look at this. Our inverse function, well, it's going to include the point 6, 3, because we know the original had 3, 6, so the inverse has got to have 6, 3. Now, the domain of our original was everything bigger than 3. So that means our range has got to be, y has got to be bigger than 3. Well, if this thing graphs down, that's not going to make this happen. So this must be positive square root. And so we know that our inverse is going to be 3, and will be inverse f of x is going to be 3 plus the square root of x minus 2 all over 2. And like we've seen before, you'll notice that the inverse and the original are reflected over the y equals x line. Okay, now let's find the inverse of a quadratic that's written in standard form. If you're asked to find the inverse of a quadratic function and it's in standard form, it has a b term, then it's probably the most difficult inverse you're going to have to use. And basically the process is we're going to rewrite it in vertex form, and then what we're going to do is do like we did in the very last example. So if it's got a b term, rewrite it into vertex form, and then switch and do everything like we did before. So let's take a look at this. The vertex is going to be negative b over 2a. And you can graph this using your graphing calculator or do this. You should know how to do both. Negative b over 2a, in this case, it's going to be 8 over 4, or 2. That's the x part of our vertex. And then if I take the 2 and substitute it in place of all the x's, I can find out what the y part of my vertex is. After we've done all our substitutions, all we've got to do is simplify, and we find out the y is equal to negative 2. So our vertex is going to be 2, negative 2. So let's remember what vertex form is. It is y equals a times x minus h squared plus k, where h and k are the vertex. So all I've got to do is plug in the values. Once I know the vertex, I already know what a is. A is 2, and it's going to be x minus 2, and then squared, and then it'll be a negative 2 at the end. That's our k. So now we've got it in vertex form. And all we've got to do is, like we did before, switch the x's and y's and then solve for y. And again, we're now, like in the last problem, the last example, we're just using opposite operations. We're going to add 2 to both sides, giving us x plus 2 is equal to 2 times y minus 2 squared over 2. And then divide both sides by 2. And we're going to get x plus 2 over 2 is equal to y minus 2 squared. And then undo the square. I square root both sides. That's going to give us plus or minus the square root of x plus 2 over 2 is equal to y minus 2. And then to get the y by itself, I add 2 to both sides, and that's going to give us 2 plus or minus the square root of x plus 2 over 2. And then hopefully you'll recall that if we take the square root function and make it positive, it's going to open up. And if I make a negative square root function, it's going to go down. And I've got to pick which one of these to use. Wait a minute. Oh, you know what? We never decided what our domain's going to be. And we've got to do that. So let's go ahead and plot our point. 2, negative 2, that's our vertex. In this case, let's use the left side. Let's use all the values that are less than 2 as our as our domain. So what we're going to end up with is a graph that looks something like this. And now that we know that we're only using the x's that are less than 2, that's going to be our domain. Well, then we can go ahead and figure out which our inverse is going to be, plus or minus. Now, if the original had the vertex of 2, -2, then the inverse must have the point -2, 2, and we can plot that. And the range has got to be the same as the other original's domain, so our range will be y is less than or equal to 2. That means that it's got to go downward, and it's going to look something like this. So a square root function that goes downward has got to be negative, so we know that this is going to be our inverse function. The next two examples are going to be rational functions. We're going to find the inverse of a couple rational functions. So the first thing is we probably need to just tell you what a rational function is. A rational function is written like a fraction. It's got a variable in the denominator. Now, we're going to spend some time working on rational functions in a later unit, so we're just going to quickly go through some things and don't get too whacked out about it. Asymptotes. Asymptotes are imaginary lines where the graph cannot happen. A vertical asymptote, well, it goes straight up and down. In this case, our vertical asymptote is x equals 0. The horizontal asymptote in this case is going to be y equals 1. So if you look on our graph in yellow, I've got the x equals 0 asymptote. The graph will not happen there. And then you'll see y equals 1. That's going to be our vertical asymptote. Now what's going to happen is, you feel free to go ahead and graph this in your graphing calculator. You're going to see something that kind of looks like this. And keep in mind, when you graph it in the graphing calculator, put parentheses around the x plus 3. Anyway, you'll notice it is a one-to-one function. Now, not all rational functions are going to be one-to-one, but the basic ones that we're going to be looking at are going to be one-to-one. So you don't got to worry too much about that part of it. So what we're going to do now is switch the f of x to a y, and then switch the x's and y's, and then get y by itself. Now, I've got to multiply both sides by y to get rid of this y in the denominator, and that's going to give me y times x is equal to y plus 3. Now keep in mind, my job is to get the y by itself. I've got y's on the left and y's on the right. So what I'm going to do is get both of the y's on the same side. So I'm going to subtract y on both sides, and that's going to give me y times x minus y is equal to 3. Now that I've got the y's on the same side, I'm going to factor out the y. So if I divide both those by y, I'm going to get y times x minus 1 equal to 3. And now all I got to do to get the y by itself is divide both sides by x minus 1. And y is going to equal 3 over x minus 1. That's going to be our inverse function. So all we've got to do now is write the notation f inverse of x is equal to 3 over x minus 1. And if you want to take and go ahead and graph that in your graphing calculator, what you're going to see is it's going to be something like this. The asymptotes have switched. So where it used to be going up to 1, well, now the horizontal asymptote is going to be 0, and the vertical asymptote is going to be 1. Anyway, you should see the inverse function look something like this. And again, go ahead and graph in your calculator. You're probably not going to have to do this by hand, at least not yet, until we go through and do more of this in the later unit. Number 8, the last example, is also a rational function, and the vertical asymptote is going to be x is equal to -4, and then the horizontal asymptote is going to be 0. And again, don't worry too much about this, because at this point you're not going to have to do any graphing. But I want to show you, if you go ahead and plug that into your calculator, y equals, make sure you put x plus 4 in parentheses, that it's going to look something like this. I'm going to go ahead and put in my x -4, that's my vertical asymptote, and then y equals 0, that's my horizontal asymptote, and the graph can't happen there. So you're going to see that it's going to kind of approach those asymptotes but never touch it. And then it's going to be on the one side and the other side. But I guess the only point, the reason I'm graphing it right now, is I want to make sure that you can see very clearly that this is a one-to-one function, that it will clearly pass the horizontal line test. So this is a one-to-one function. Its inverse will also be a function. I don't have to worry about restricting the domain in any way. So now if I replace the f of x with a y and then switch to x's and y's, I end up with this. And in this case, I'm going to multiply both sides by y plus 4. And that's going to give me y plus 4 times x is equal to 3. Now, I'm not going to distribute this because keep in mind my job is to get the y by itself. So all I'm going to do is divide both sides by x. And see, that's going to leave me with y plus 4 is equal to 3 over x. And now all I got to do is subtract 4 on both sides to get the y by itself. I'm going to end up with y is equal to 3 over x minus 4. And then when I write that in notation, f inverse of x is equal to 3 over x minus 4. Now I'm going to graph it real quick. I suggest you put it in your graphing calculator and compare and see that they look pretty much like this. Okay, now here's some things to remember. When you're finding the inverse of a function algebraically, I'm not going to read all these, so pause it and make sure you get these down. But keep in mind, if you need to find out if a function is one-to-one, graph it in your graphing calculator and make sure it passes the horizontal line test. If it's not going to pass, then we need to restrict the domain. Quadratics are never one-to-one, so always restrict the domain. And a good way to do that is to look at the vertex. We're going to switch the x's and y's and solve for y. If quadratics don't have a b term, well then that's easy. All you do is do inverse operations to get y by itself. But if it does have a b term, you're going to have to put it in vertex form and then go from there. And then make sure you always use this f-1 notation to show you've got an inverse function. Okay, that's all I got for this one. I hope that helps, and thanks for watching.